Welcome to EPG Pathshala program in Linguistics. We are going to discuss a module from the course An Introduction to Computational Linguistics and Speech Processing. The coordinator of this course are Professor Pramod Pandey from JNU and Professor Deepti Misra Sarma from IIIT Hyderabad. The module title is HMM based speech synthesis system, that is Hidden Markov Model based speech synthesis system. The author of this module is Professor Hemant Pandey. I am Amardeep Kumar Singh, School of Computer and System Sciences, JNU, and I am going to present this module on behalf of Professor Patil. Let's get into the discussion. Outline of the module named HMM based speech synthesis system, that is Hidden Markov Model based speech synthesis system. In this module, we are going to discuss firstly the motivation for statistical parametric speech synthesis system. Then one of the statistical parametric speech synthesis system, which is HMM based speech synthesis system. We are going to discuss the fundamentals of HMM, the diagram of HTS procedure, which is the HMM based speech synthesis system, then spectral parameter extraction, then excitation parameter extraction, context dependent modeling, parameter generation from HMMS, and synthesis filter. Then after describing the method, we will be discussing a case study which is done on Gujarati language. At the end of this module, we will be discussing the experimental setup and the evaluation procedures done on this synthesis system. Let's get into the whole discussion in detail. So let's start the module. So till now what we have done is we have described three kind of synthesis system, or rather the approaches. First one is model based speech synthesis, which is a simplified model of a speech production which is driven by the rules. For example, formant synthesis, articulatory synthesis, etc. fall in this category. In formant synthesis, fundamental frequency, voicing and noise levels are varied over time to synthesize a speech waveform artificially. This method is also known as a rule-based method. The second one is concatenative synthesis, which we have described in the earlier module. In this method, at the time of synthesis, appropriate speech sound units are selected from pre-recorded speech database and concatenated in runtime. Since these speech sound units are selected from natural speech, this method provides high quality and naturalness in synthetic speech. Due to limited vocabulary and usually one TTS voice, this method is suitable for limited domain speech synthesis. However, it requires 8 to 10 hours of speech data for unrestricted TTS synthesis method. The third one is statistical parametric speech synthesis. Instead of storing entire speech database in this method, statistically meaningful model parameters are stored and used to synthesize waveforms. Hidden Markov model based speech synthesis system comes under this method. So the generalized statistical framework of Hidden Markov model has been applied successfully to the automatic speech recognition problems and are currently applied in speech synthesis applications. In this module, HMM based speech synthesis system for TTS is explained briefly, and an application to Gujarati language has also been explained. So let me tell you a few motivation behind using the SPS synthesis system. To build a unit selection system on a single speaker, about 8 to 10 hours of speech database is required. In addition, syllable or phoneme coverage in database is very uneven. Apart from this, in concatenative approach, a system will recreate units from pre-recorded speech data. Furthermore, in this approach, we are effectively memorizing the data, whereas in a statistical approach, we are attempting to learn general properties of the data. The main advantage that arises from statistical models is that it requires very less memory to store the parameters of the model than concatenative approach. Secondly, we can modify model to convert original voice into another voice. Although current TTS system can synthesize voice with high quality, however, they cannot synthesize speech with various voice qualities. In concatenative approach, to obtain various voice qualities in synthesis system, very large number of speech data is required. In order to construct inexpensive speech synthesis systems that can generate various voice qualities, an HMM-based speech synthesis system was proposed. The main motivation behind this application is to start building TTS system for visually challenged people who do not know English. Hence, visually challenged people who know only their mother tongue can utilize this TTS technology. We will be giving an example of Gujarati language at the end of this module as well. Now we will describe the main part of this module, which is the HMM based speech system, speech synthesis system, which is also known as HTS. So firstly, let me describe the fundamentals of HMM. A hidden Markov model can be considered as a finite state machine which generates a sequence of discrete observations. At every time HMM changes state corresponding to a state transition probability and then generate an observation data according to the output probability distribution of the current state. HMM can be denoted by lambda equals to A, B and the pi, where A is the transition matrix, B is the state transition probability matrix, and this pi is the initial state probability distribution. A real world application can be modeled by understanding three basic problems of HMM. The problem 1, given the observation sequence and HMM defining by lambda, how do we efficiently compute the probability of observation given model? The problem number 2, given the observation sequence and HMM defined by lambda, how to find best possible state sequence Q? The problem 3 is, given the training data, how do we adjust model parameters such as to maximize this probability of O given lambda? Now, solutions of these three problems are explained in detail in the research papers. However, in this module, we won't be describing these solutions in detail. The analytical solution of the above problem mentioned is not possible. However, we can adjust model parameter in such a way that it maximizes the likelihood. Now, Baum-Welch algorithm is used to solve above mentioned problem, which is expectation maximization algorithm for HMMs. Now let me show the functional block diagram for building HTS. As you can see, there are two parts. One is training part and the other is synthesis part. In training part, spectrum and excitation parameters are first extracted from speech database, mel frequency, Spectral coefficients and their dynamic features, that is delta and double delta features are generally taken as spectrum parameters, and log f0 and its dynamic features are taken as excitation parameters. Then these features are modeled by context dependent HMMs. Here spectrum, excitation and duration are going to be modeled in a unified framework. The second part is synthesis part. First given sentence which has to be synthesized, it can be from English language or any other Indian language, for example Hindi, Gujarati, etc., for which we are interested in building TTS system. Its corresponding utterance is converted to context dependent phoneme sequence. Then according to the phoneme sequence, an utterance HMM is constructed by concatenating context dependent HMMs. Then state duration of HMMs is determined. Then using speech parameter generation algorithm, spectrum and excitation parameters are generated. Finally, using MEL log spectrum approximation, which is MLSA, filter speech waveform is generated. Now let me describe how this spectral parameter extraction works. So from speech waveforms, spectral parameters are extracted first. In this work, MFCC and their dynamic features are taken as spectral parameters. Here in our experiment for the Gujarati languages, we have taken 35-dimensional MFCCs per frame. Now the question is, why do we require such huge number of MFCCs per frame for synthesis as compared to these used in speech recognition task? For speech synthesis, we have to synthesize waveform from those MFCCs, whereas for recognition, we have to recognize which phoneme was there. Hence, we require only 10 to 20 MFCCs per frame in HMM-based speech recognition, whereas for synthesis, we require 25 to 40 coefficients per frame. Researchers have done extensive studies on this question and found that if we decrease number of mel-frequency spectral coefficients per frame in synthesis, quality of synthesized speech will get affected. Now, see how excitation parameter extraction works. So, the excitation parameters are extracted from speech waveforms. Fundamental frequency, which is f0, is taken as excitation parameter in HTS. Generally, log f0 is taken as excitation parameter. Now the question is, why to take logarithm of f0? This can be explained from the plots, as you can see in this figure. So there you can see a speech waveform corresponding to f0 pattern, then the PDF of f0, then the PDF of speech utterance. As you can see, the 4 graphs together in this figure, which are shown by A, B, C and D. So these figures were generated by considering a general speech sample in Gujarati language. From these plots, we can see that probability density function is approximately Gaussian. This is one of the reasons for taking a logarithm for f0 instead of f0. So in addition, sensation to sound is logarithmic. Therefore, logarithm of f0 is preferred over just f0. And this gives you the answer to the question. Now let me describe the context-dependent modeling. So let me describe the context-dependent modeling. Here we will address the motivation for building context-dependent HMMS. Now at the time of speech synthesis, phoneme level concatenations are not really good for listening. In order to cover suprasegmental information, context-dependent modeling concept was taken. Hence, instead of having single phone model, we will use phone model with its contextual factor information. The most common way to do this is to use triphone or pentaphone models, which are not models of 3 phones. However, single phone models in the context of proceeding and following phone. Hence, for n phones, there will be less than n cube triphones. So now in this context, the research issue is we do not have enough data which covers sufficient amount of instances for every triphone. Sometimes we have insufficient instances to train model, which is called low occupancy, and sometimes not a single instant, which is called zero occupancy. Now what could be the solution of this? The solution to the problem is to cluster the data. Now to deal with the low occupancy and zero occupancy problems, we can find examples that are near to the known examples in acoustic space, and also clustering by use of some common properties of phones. Common properties of phones include group of vowels, nasal, fricatives, stops, etc. The easiest way of performing such clustering task is to use decision tree based clustering. Now let me show the decision tree based context clustering. So you can see on your screen the context dependent modeling, decision tree based context clustering. This figure is an example of decision tree based context clustering, whether current phone is vowel, if yes, whether it has silence at its right position, and so on. In this manner, it will cluster each phone. Now, to cluster data with decision tree based context clustering method, we require question for each node. To get this, we will build a set of questions. This process is known as question set preparation in HTS literature. For our system, we have used pentaphone clustering for better representation of supra-segmental effects. Hence, our question set will have center, left, right, left to right, right to right, etc. Following are typical questions from our question set. Is C a vowel? Is R silence? Is L nasal? Is R fricatives? Is LL plosive? Is RR silenced? So symmetrical triphone contextual factors, that is preceding and following phonemes, are symmetrical pentaphoneme contextual factors are usually preferred in preparing question set. Asymmetrical contextual factors also affect the quality of speech synthesis. Moving on, parameter generation from HMMS. So let us see how the parameter is generated from HMMS. The parameters are generated from HMMS using a speech parameter generation algorithm. So the problem is, for given sentences which has to be synthesized at the time of synthesis, problem is to obtain an observation sequence denoted by O, which consists of spectral parameters and excitation parameters from lambda HMM corresponding to given sub-word unit sequences, that is context dependent level sequences, such that it maximizes posterior probability with respect to O. Now the solution of this problem of parameter generation is worked out by solving a word sequence problem where we maximize the argument of the probability over O given lambda and T. To find the observation sequence from given utterance, first we have to find best state probability sequence such that it maximizes the probability, and then observation sequence, that is O. Thus, by solving above two problems, we can find optimal observation sequence, which is given by O. Moving on, let me describe the synthesis filter. So synthesis filter works as a speech vocoder which convert spectral and excitation parameters into speech waveform. In our HTS developed for Gujarati language, Mill-log spectrum approximation filter is used as a synthesis filter. Main work of MLSA filter is to synthesize a speech waveform from spectral parameters and excitation parameters, which is generated as an observation sequence from a speech parameter generation algorithm. The spectral envelope of a speech can be represented efficiently by the log magnitude spectrum on the nonlinear frequency scale, which is close to MEL scale, called as MEL-log spectrum. The MLSA filter is the first filter to approximate MEL-log scale. The MFCC gives good and compact representation for psychoacoustically relevant information. Since the representation on MEL scale, the coefficient cannot be used in spectral vocoder, frequency unwarping needed. In addition, simple spectral vocoder requires the computation of the impulse response of a spectral envelope, which is not computationally efficient. From MEL spectral parameters and excitation signals generated from pitch contour will generate synthesized speech. Now we'll describe the case study which is done on adapting to Gujarati language. So I'll describe here briefly the introduction to Gujarati language, Gujarati speech corpus development, transliteration and its related issues, selection of speech sound units for speech segment, and then the classification of Gujarati characters. So Gujarati is one of the official languages of India, as you all know. It is primarily spoken in the Indian state of Gujarat. Gujarati is an Indo-Aryan language and has evolved from Sanskrit. Gujarati is a variant of Devanagari script. Unlike other Devanagari scripts, Gujarati character doesn't have horizontal line running above it. For example, if you write Gujarat in Gujarati, by using the scripts you can write it without using the overhead straight line. So not due to the number of speakers, but due to less availability of resources in terms of standard database, Gujarati may be considered as a low-resourced language. Similarly, there are other low-resourced Indian languages such as Hindi, Marathi, Punjabi, etc. So how the Gujarati speech corpus is developed? Due to unavailability of Gujarati standard corpus for the speech synthesis application, the first task in this case study was to develop a speech database for Gujarati language. As discussed in earlier module, we have collected several texts from various sources like news, blogs, stories, etc. We recorded these texts from professional native female and native male voices over artists. Details of the corpus are mentioned in the research papers used for this module preparation. Now the third step, where we will describe the transliteration and its related issues. For this purpose, you can see a table on your screen which shows the mapping from Gujarati UTF-8 to common phone set. Here we can see the level IPA, Gujarati, the Gujarati translation, the label, and then again the IPA, the Gujarati translation, and then again the level IPA followed by the Gujarati translation. So this is a mapping from the Gujarati UTF-8 to common phone set. Here the Perl script was written to do the transliteration. Following are the major steps involved in the Perl scripts, and the steps are: a text is converted into Unicode characters, then a sentence is converted into array of words, and words are converted into syllables. Then from each syllable pairs, 3 characters are taken as Unicode characters for Gujarati language, which have length of 3 characters. In addition, the issues of swa deletion and anuswara are included in scripts which are explained. Now using hash table, each Unicode is mapped to common phone set. For reference, you can see the next table, which is the IPA chart for Gujarati consonant. Here we can see the IPA consonants in the first column, then the place of articulation, which are basically bilabia, labiodenta, alveolar, post-alveolar, retroflex, palatal, velar, and glottal. You can see there Gujarati transliteration as well, and on the left you can see the manner of articulation, that is whether it is plosive, nasal, trill, tap, flap, fixative, approximately, or laterally approximate. Now there is another figure which you will see as the IPA chart for Gujarati vowel. Here same, based on the height of tongue, the vowels are shorted and the position of the tongue is also mentioned. You can see the table. Now for this experiment, I will describe the experimental setup used and the evaluations. In order to build HTS system for Gujarati language, we have taken in total 4 hours of phoneme leveled data from a male and a female speaker, out of which we have developed following HTS systems for Gujarati language. We have taken 105 dimensional male generalized, Spectral coefficients per frame, 3-dimensional log F0 and pentaphone contextual factor. We have built 8 total different HTS systems on male and female speech database with training data increases from 1 hour to 4 hours. In the next subsection, we will discuss the subjective evaluation of HTS voice. Now here we can see the experimental results in this slide. Now you can see the speech intelligibility, and also you can see the MOS of HTS system built using male Gujarati speech database. The experimental results for this experiment is being shown on your screen. You can see it. The size of HTS runtime engine built for the Gujarati language is given by this table. You can see the separate sizes for the female voice and the male voice categorized into 1 hour, 2 hour, 3 hour or 4 hour category. And this one is the locating issue in the system which is being shown as part of the experimental results. So though our synthesized speech generated using HTS approach has better speech intelligibility, however its naturalness is lost significantly. Hence, to analyze this issue, let's have a look at HTS based synthesized speech and corresponding natural speech, as you can see in this figure shown on your diagram. These figures show a speech waveform and its corresponding pitch contour for natural and synthetic speech respectively. In the two figures that you can see on your screen, the first one, pitch contour portion between orange and the red line contains same word. However, shape of their speech pattern is different, due to which it sounds like unnatural. In our system building, for one particular frame, we are taking only one value of log F0. This might be one of the reasons for losing naturalness in the synthesized speech signal. In this module, we have understood the basic HMM based speech synthesis system, and we have also understood how to adapt the generalized HMM based speech synthesis framework, that is the HTS framework, into any other language. And we have also shown the case study of adapting this framework for Gujarati language, which is one of the Indian language. Lastly, we have also shown the quality evaluation of such a synthesis system, the framework, and then the possible issues behind the lower naturalness of this framework is also explained. In the next module, we will be describing the evaluation processes of HTS voice system or any text-to-speech synthesis system, voice system. So let's move on to next module. Till then, thank you.